Science isn't just facts, it's stories. If I told you the stuff sitting quietly on your fries belongs to a metal that can lose its mind in water, you would probably assume chemistry has a drinking problem. But that is sodium for you. It helps your nerves fire, keeps your muscles working, and makes food taste less like sadness. Yet in pure form, sodium is a soft silver metal that reacts so aggressively with water that chemists store it like it owes the universe money. And that is the magic trick of the periodic table. The same element that helps season your popcorn can also skitter across water, throw off heat, make hydrogen gas, and sometimes burst into a dramatic yellow flare. Not because sodium is evil, just because it has the emotional stability of one lonely outer electron. Today, we are breaking down why sodium is so reactive, why your body needs it, why salt is safe while sodium metal is absolutely not, and why chemistry keeps making ordinary things sound fake. Sodium is element 11 on the periodic table with the symbol Na. And yes, that symbol looks like it showed up late and ignored the dress code. It comes from the older name natrium, which is why sodium gets to confuse everyone on sight. In pure form, sodium is a soft, silvery metal. Not strong, heroic metal soft. More like you can cut it with a knife, and now you are suddenly rethinking metals soft. Freshly cut sodium looks bright and shiny for about 5 seconds. Then it starts reacting with oxygen and moisture in the air, and that clean metallic surface quickly turns dull. So right away, sodium is already weird. Most people picture metals as tough, stable, maybe a little dramatic, in a blacksmith sort of way. Sodium is more like a nervous guy at a party who hears one awkward comment and immediately makes it everybody's problem. That instability comes down to its electrons. Sodium has 11 electrons total, and the important part is the one sitting out on the edge, all alone in the outer shell. Atoms like stable outer shells, and sodium's easiest path to peace is to get rid of that one electron as fast as possible. That is the whole story, really. One outer electron, one terrible sense of boundaries, one non-stop urge to hand that electron to almost anything willing to take it. That makes sodium an alkali metal, part of the group on the far left side of the periodic table. These elements are known for being highly reactive, especially with water, and sodium fits right in. It is more reactive than lithium, less reactive than potassium, and just unstable enough to make chemistry demonstrations look like the periodic table is trying to go viral. This is also why you never find chunks of pure sodium just lying around in nature. It is too reactive. If sodium is out in the real world, it almost immediately bonds with something else. Oxygen, chlorine, sulfur, carbon, water, something. Sodium does not stay single for long. That brings us to the most famous sodium stunt of all: water. Put a piece of sodium metal into water, and the reaction starts almost immediately. Sodium gives up its outer electron, water molecules get torn apart, sodium hydroxide forms, hydrogen gas is released, and a lot of heat comes out in the process. That heat matters. Sodium melts at a pretty low temperature for a metal, so the heat from the reaction can melt it into a shiny little blob. That is why sodium often looks like a tiny silver bead racing around on the surface of the water. It is not swimming. It is basically being pushed around by its own reaction, surrounded by heat, gas, and rapidly forming chemicals. The whole thing looks less like science and more like the metal is trying to flee the consequences of its own decisions. Sometimes that released hydrogen gas gets hot enough to ignite. When that happens, you can get a yellow flame, which is fitting because sodium has a very distinctive yellow glow when its atoms get excited. Sodium is the rare element that can be both chemically reckless and weirdly photogenic. And no, sodium is not angry at water. Chemistry videos love giving elements personalities because it makes them memorable, and honestly, that works. But what is really happening is simpler and more elegant. Sodium is in a high-energy, unstable situation, and water gives it a very easy path to become more stable. That is the secret beneath a lot of chemistry. What looks dramatic is often just nature taking the fastest route downhill. So if sodium metal reacts this strongly, why can you pour salt on dinner without setting off a kitchen crisis? Because table salt is not sodium metal. Table salt is sodium chloride, a compound made when sodium gives an electron to chlorine. Once that happens, sodium becomes a positively charged ion, chlorine becomes a negatively charged ion, and the two lock together in a stable ionic structure. And that changes everything. This is one of the biggest lessons in chemistry. Elements and compounds are not the same thing. Not even close. Pure sodium metal is highly reactive. Pure chlorine gas is dangerous. Put them together in the right ratio, and now they are sitting on your French fries, pretending they were never a problem. Chemistry is full of these ridiculous plot twists. And sodium does not just show up in salt. It shows up all over your life. Your body depends on sodium ions for some of its most important functions. Nerve cells use sodium to help carry electrical signals. Muscles rely on sodium to contract properly. Your body also uses sodium to help regulate fluid balance. So yes, sodium is essential. That does not mean the more the better, because biology loves nuance and hates easy slogans. You need sodium to live, but too much dietary sodium is linked to high blood pressure in many people, which is why sodium ends up in both nutrition advice and chemistry demos for completely different reasons. Inside your cells, sodium is part of one of the most important little machines in biology, the sodium-potassium pump. This protein uses energy to push sodium out of cells and pull potassium in. That difference in ion levels helps create the electrical gradients that let nerves fire, muscles move, and brains do things like remember where you left your phone while holding your phone. Without sodium gradients, your nervous system does not work properly. So sodium is not just that thing in salty food, it is part of the electrical language of your body. And outside the body, sodium compounds are everywhere. Baking soda is sodium bicarbonate. Washing soda is sodium carbonate. Lye is sodium hydroxide. Sodium compounds show up in soap making, glass production, paper processing, water treatment, and a long list of industrial chemistry that quietly keeps modern life from falling apart. That is one reason sodium is such a great element for this series. It is chaotic enough to be fun, but practical enough to matter. Even the oceans are packed with sodium ions. Over long periods of time, rocks on land break down through weathering. Rivers carry dissolved minerals to the sea, and sodium is one of the major ions that builds up there. That is a big reason seawater is salty. So sodium is not just on your dinner table. It is in your blood, in the ocean, in factories, in food chemistry, in cleaning products, in glass, and in some of the most basic systems that make life and civilization function. Not bad for a soft metal that cannot be trusted near a sink. There is also a nice bit of history here. Pure sodium was first isolated in 1807 by Humphrey Davy, who used electricity to force it out of molten compounds. That is such a perfect chemistry moment. Sodium was so eager to bond with other elements that humans had to use electrical brute force to pull it out and say, "No, sit here by yourself for 1 second so we can look at you." Even today, industrial sodium production relies on electrolysis. That means using electricity to separate sodium from molten sodium chloride. You cannot just go mine shiny sodium nuggets out of the ground like some kind of periodic table pirate. Sodium is too reactive for that fantasy. And sodium is still relevant in newer technologies. Lithium gets most of the battery fame because lithium-ion batteries run phones, laptops, and electric vehicles. But sodium-ion batteries are getting attention because sodium is much more abundant and cheaper, even if it is not always the best fit for every battery job. So sodium is not some outdated lab curiosity. It is old-school chemistry, modern industry, biology, history, and future technology all jammed into one gloriously unstable package. And then there is sodium's color. If you have ever seen older streetlights casting that eerie yellow glow, you have met sodium vapor lamps. Excite sodium atoms, and they produce a very strong yellow light that is instantly recognizable. So the element is not just chemically dramatic, it is visually branded. Of course, sodium's reputation also suffers from one of the classic chemistry mistakes. People hear that sodium is in salt, then hear that sodium metal reacts strongly with water, and suddenly it sounds like dinner should be treated like a hazardous materials incident. But again, compounds matter. The properties of a compound can be completely different from the properties of the elements that made it. That is not a loophole. That is chemistry. It is also what makes the world interesting. Take sodium, a highly reactive metal. Pair it with chlorine, a dangerous gas. The result is table salt, one of the most familiar substances on Earth. That is not just useful chemistry. That is chemistry showing off. And sodium belongs to a family with a clear pattern. As you move down the alkali metals, the atoms get larger, and that outer electron is held less tightly. That is why reactivity generally increases as you go down the group. Lithium reacts, sodium reacts more, potassium reacts even more dramatically. So sodium sits in a very convenient sweet spot. It is reactive enough to be exciting, but common enough to matter in daily life. It is the perfect middle child of important, dangerous, and everywhere. That makes it a fantastic gateway element. Because once you understand sodium, you start understanding bigger chemistry ideas: electron transfer, ion formation, chemical stability, reactivity trends, compounds versus elements, and why one tiny change in atomic structure can completely rewrite the behavior of matter. That is the real reason the periodic table is so addictive. Tiny atomic differences create wildly different outcomes. One electron here, one shell there, and suddenly you go from harmless gas to brittle crystal to soft metal to essential nutrient to water reactive menace. And sodium checks every box. It is in your body. It is in the sea. It is in your kitchen. It is in industrial chemistry. It glows yellow. It reacts with water. It has a bizarre symbol. It is one of those elements that feels made up until you realize it is woven into half the world around you. Honestly, sodium is a great reminder that the universe did not build reality to be intuitive. It built reality to be interesting. So the next time somebody casually reaches for the salt shaker, just remember they are handling the domesticated version of a metal that, in pure form, would absolutely not be invited back for a second dinner. That is sodium. Soft, common, essential, unstable, useful, and just dramatic enough to make chemistry feel less like memorizing facts and more like watching matter reveal its personality. And if sodium is the metal that goes wild in water, the next logical question is this. What happens when you look at the greenish gas that teams up with sodium to become table salt? Because chlorine is somehow both worse and more useful than you think.